Hello friends, and welcome to YouTube channel on Engineering Mathematics by Dr. Navneet. In this video lecture, we are going to discuss about the inverse Laplace transformation concept. So in this video lecture, our main focus is on a definition of inverse Laplace transformation, and then we are discussing the standard results which are related to the inverse Laplace transformation, and I am going to explain all these standard results with the help of simple examples. So this is the things which we are learning in this lecture. So now let me start this concept with the definition of Laplace transformation. So first let's define the Laplace transformation. So first thing is definition. So we know the definition of Laplace transformation. So definition of Laplace transformation is if Laplace transformation of f of t, if Laplace transformation of f of t is equal to integration 0 to infinity e raised to minus st f of t dt. So we know that this is the definition of Laplace transformation, and we are denoting this by phi of s. So this is the definition of Laplace transformation. Then so this value, then the value f of t, then f of t is called the value f of t is called the inverse Laplace transform. So then f of t is called the inverse Laplace transform of phi of s. So this is called as the inverse Laplace transformation of phi of s, and can be denoted by, or we call this as, can be denoted as inverse Laplace transformation of phi of s is equal to f of t. So this is the definition of inverse Laplace transformation. So that means in this definition of Laplace transformation, so this function f of t is called as the inverse Laplace transformation of phi of t. So this is the simple definition of inverse Laplace transformation. Then for solving example based on inverse Laplace transformation, so there are 5 different methods. So let's discuss the concept which is called as methods of finding inverse Laplace transformation. So let's discuss the methods which are related to the inverse Laplace transformation. So actually there are 5 different methods are there for finding the inverse Laplace transformation. So in short, we are abbreviating this Laplace transformation as LT. So now first method for finding this inverse Laplace transformation is called as the standard result. So this is the first method to find out the value of inverse Laplace transformation. Then second method is called as second shifting theorem. So this is the second method for finding the inverse Laplace transformation. Then third method for finding the inverse Laplace transformation is called as partial fraction expansion. So this is the fourth method. Then third method. Now let's discuss the fourth method. So fourth method is about the convolution theorem. So this is the fourth method, and one more method is there. So this is called as differentiation of the value phi of s. So these are the 5 standard methods for finding the inverse Laplace transformation. So let's learn all this method one by one. So in today's lecture, in this video lecture, we are going to discuss the first method, which is called as how to find the inverse Laplace transformation by standard results. So now let's discuss the first method, inverse Laplace transformation by standard result. Now friends, let's discuss the first method. So for finding the inverse Laplace transformation, first method is by standard results. That means inverse Laplace transformation by standard results. So let's discuss the standard result first. So we know the first result. So first result is that Laplace transformation of e raised to at. So we know the value of this term, so which is 1 upon s minus a. So this is the standard result of Laplace transformation. So therefore we can write the inverse Laplace transformation of 1 upon s minus a as, so this is e raised to at. That means Laplace transformation of 1 upon s minus a is equal to e raised to at. So where this L inverse, so this term, so this L inverse is called as inverse Laplace transformation operator. So this is called as inverse Laplace transformation operator. So this is the first standard result. So this first standard result says that inverse Laplace transformation of 1 upon s minus a is equal to e raised to plus at. That means whenever some constant term is subtracted from the parameter s, then this result is applicable. So now to discuss this, so first example is that, so if we wish to find the inverse Laplace transformation of 1 upon s minus 4, so then answer to this question, if we compare this part with this term, then the value of a is 4, then we can write its answer as e raised to 4t. So now second example, inverse Laplace transformation of suppose 1 upon s this is minus, suppose this is 10. So we can write this as e raised to 10t. So this is the first result which is related to the standard result by inverse Laplace transformation. Now second result, we know that Laplace transformation of e raised to minus at. So Laplace transformation of e raised to minus at is 1 upon s plus a. So therefore we can write the inverse Laplace transformation of 1 upon s plus a is equal to e raised to minus at. So this is the second standard result. So now to understand this result, so difference between this first result and second result is that, so in first result we get minus sign in between s and a, whereas in second result we get plus sign in between s and a. So now if we replace this minus sign by plus, then we get this as e raised to minus 40. Again, if we change minus to plus, then we get this as minus. Or second example, so if we wish to find out the inverse Laplace transformation of 1 plus 2, so we can write this as e raised to minus 2t, because value of a is 2, and we can write this as e raised to minus 2t. Similarly, inverse Laplace transformation of 1 upon s plus 5, so we can write this as e raised to minus 5t. So now this is about the second result. Now let's discuss the third result, inverse Laplace transformation of 1. Laplace transformation of 1, we know that the value of this term is 1 upon s. Therefore, if we find the value of inverse Laplace transformation of 1 upon s, then its value is 1. So that means whenever 1 upon single s term is present in the denominator and power of this s is 1, then we can directly write the inverse Laplace transformation of this value as 1. So now this is the straightforward result, so there is no example. So now let's discuss the fourth standard result. We know that Laplace transformation of sine of at. So this Laplace transformation is a upon, this is s square plus a square. Therefore, so in this term a is constant, so if we take this L to this side, then we get this as inverse Laplace transformation of 1 upon, this is s square plus a square, so we can write this as 1 upon a into sine of at. So after taking this a to the right side, so now we get this as the result. Now to understand this fourth result, now let's discuss this fourth result with the help of some standard result. So now if we wish to find out the inverse Laplace transformation of, this is 1 upon s square plus 16. So we can write this as inverse Laplace transformation of 1 upon s square plus 16 is the square of 4, so we can write this as 4 square. So 4 4 the 16. So now this equation is in our standard form, 1 upon s square plus a square, where the value of a is 4. So we can write its inverse Laplace transformation as 1 upon 4 into sine of 40. So 1 upon a into sine of 80. So where the value of a is 4. So that's why this is 1 upon 4 into sine of 40. So similarly, if we wish to find out the inverse Laplace transformation of 1 upon s square plus 25. So this is the value of a square plus a square, where the value of a square is 25. That means value of a is 5. So we can write the value of a is equal to 5. So we can directly write this inverse Laplace transformation as 1 upon 5 into sine of 5t. So this is the fourth result. Now let's discuss the next result. Laplace transformation of hyperbolic sine function is known to us. So this value is a upon, this is s square minus a square. Therefore, inverse Laplace transformation of 1 upon s square minus a square. So this value is 1 upon a into sine h of 80. Now here question is that, so what is the difference between fourth and fifth result? So now here this is sine term and this is hyperbolic sine function. For sine term, middle sign is plus, whereas for hyperbolic function, this middle sign in the denominator is minus. So same result is there, only when sign is minus, then use the hyperbolic function. So now to understand this concept, let's take the next example. So now example is, suppose if we wish to find out the inverse Laplace transformation of 1 upon s square minus, suppose this is 9. So we know that this is of the type s square minus a square. So this is of the a square minus a square, where the value of a is 3, because 3 square is 9. So moreover we can write this as inverse Laplace transformation of 1 upon s square minus 3 square. So according to the standard result, value of a is 3. So we can write this as 1 upon 3 into sine h of 3t. So this is the simple example which is related to the standard result number 5. Now let's discuss the sixth result, Laplace transformation of cos of 80. So this is the standard result we know. So according to this standard result, we can write this as s upon s square plus a square. So this is the Laplace transformation of cos of 80. So therefore, if we take the inverse Laplace transformation of s upon s square plus a square, then this inverse Laplace transformation is cos of 80. So this is the value of cos of 80. Now to understand this concept, so we can take the example as, so to find out the inverse Laplace transformation of s upon s square plus, suppose this is 64. Suppose this is 64. Now if we observe that this, if we compare this example with the standard result, numerator is s value. So this is s square plus 64. So we can write this as inverse Laplace transformation of s upon s square plus 8 square. So that we get this standard form where the value of a is 8. So according to this formula, so we can write this as cos of 80. Cos of 80. Now one more example. So inverse Laplace transformation of s upon s square plus 16. Again, this equation is in this form where the value of a is 4. So a is equal to 4. 4 square is 16. So we can write this as inverse Laplace transformation of s upon s square plus 4 square, which is cos of 4t. So cos of 40. So in this way, we can easily find out the Laplace transform, inverse Laplace transformation of s upon s square plus a square. Now seventh result is Laplace transformation of cos h of 80. So this is hyperbolic function. So we know that the standard result is s upon, this is s square minus a square. Therefore, if we take the inverse Laplace transformation of the term, this is s upon s square minus a square, then its value is cos h of at. That means this is hyperbolic function. Now observe that, so difference between this 6th and 7th result is that, so when the sign of this term s square and s square, that means middle sign of this s square and s square is plus, then cos term is there. When this middle sign between these two terms is minus, then use the hyperbolic function. Otherwise result is same, only difference is in the sign. So now to understand this result number 7, let's take the simple example. So now example is, suppose to find out the inverse Laplace transformation of, this is s upon s square minus 16. So now here this example, if we compare with the standard result, then where we get the value of a as 4, because 4 square is 16, so we can write this as inverse Laplace transformation of s upon s square minus 4 square, which is cos h of 4t. So we write here hyperbolic cos function because this middle sign between s square and s square is minus. So this is minus sign, that's why hyperbolic cos function. Similarly, to find out the inverse Laplace transformation of s upon s square minus 9, if we compare this with the result, then value of a is 3 because 3 square is 9. So we can directly write the answer of this term as cos h of 3t. So this is the 7th standard result. Now let's discuss the 8th standard result. So before going to this 8th standard result, so let's try to understand result number of 4, 5, 6 and 7. So in this 4 result, denominator term is near about same. Everywhere s square, 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 s square is there. So now whenever any constant term or 1 is present in the numerator, then use sine term. Whenever parameter s is available in the numerator, then use cos term. That means when we have to use the cos term and when we have to use the sine term, when 1 is present in the numerator or any constant term is present in the numerator, then use the sine and hyperbolic sine function. So then if for cos and hyperbolic cos function, so parameter s is present in the numerator. Otherwise denominator term is near about same. So try to understand this result so that we can easily apply this result. Now we know the next result, Laplace transformation of t raised to n, which is n factorial upon s raised to n plus 1. So this is the result. So therefore if we take the inverse Laplace transformation of 1 upon s raised to n plus 1, so then this inverse Laplace transformation is 1 upon n factorial into t raised to n, because this n factorial is constant term. So we can take this on the right side. So we can write this as 1 upon n factorial into t raised to n. Now to understand this standard result number 8, let's take the next example, which is simple one. So example is, suppose if we wish to find out the inverse Laplace transformation of 1 upon s raised to 8. So if we compare this example with the standard result, so we can write this as inverse Laplace transformation of 1 upon s raised to, so this is 8. This 8 value stand for n plus 1. That means the value of n plus 1 is equal to 8. So we can write the value of n as 8 minus 1, which is 7. So we can write this as 7 plus 1. So this is the simple technique. Actually this is very simple. Now we can write the value of n is equal to 7. So we get here. So again if we compare this with this, then we get the value of n as 7. So we can write answer up to this term as t raised to n. That means t raised to 7 upon 7 factorial. Upon n factorial means this is 7 factorial. But friends, this result is applicable when n is positive. So please try to understand, this result is applicable only when the value of n is positive. So now one more result is there. So Laplace transformation of t raised to n is equal to, this is gamma function of n plus 1 upon s raised to n plus 1. So therefore we can write this as inverse Laplace transformation of 1 upon s raised to n plus 1 is equal to 1 upon gamma function of n plus 1 into t raised to n. So again here question arise when we have to use result number 8 and when we have to use result number 9. So when the value of n is positive, then use result number 8. When n is in the form, suppose n is in the form p upon q, at that case use result number 9. So now let's take the next example, so to understand this result number 9. So example is, so to find out the inverse Laplace transformation of, suppose this is 1 upon s raised to 3 by 2. So s raised to 3 by 2. So here n is of the form, so here the value of n is of the form p upon q. So whenever n is of the form p upon q, use result number 9. So according to this result number 9, so we can write this as inverse Laplace transformation of. So write this as n plus 1. So here the value of n plus 1 is 3 by 2. So value of n plus 1 is 3 by 2. So if we try to find the value of n, we get this as 3 by 2 minus 1. So we get this as 1 by 2. So this value is 1 by 2. So now we can write this as 1 upon s raised to 1 by 2 plus 1. S raised to n by 2 plus 1. So in this way, this is a simple technique to find out the value of n, or we may directly by orally understanding this concept, we may write directly value the value of n as 1 upon 2. So now we can write this in the form of s raised to n plus 1, where the value of n is 1 upon 2 now. So if we compare this with the standard result, then value of n is 1 by 2. So we can write this as 1 upon gamma function of 1 by 2 plus 1. So this is gamma function into t raised to n. T raised to n means this is t raised to 1 by 2. So friends, so these are all 9 standard results are there which are related to the inverse Laplace transformation. So these results are very important. So whole concept of this inverse Laplace transformation depend on this 9 standard result, along with one property that is called as linearity property for the inverse Laplace transformation. So let's discuss the next concept, which is called as linearity property of the inverse Laplace transformation. So now next property is linearity property of inverse Laplace transformation. So I will use the abbreviation as ILT. So this ILT stand for inverse Laplace transformation. So next is linearity property of the inverse Laplace transformation. So this property says that if K1 and K2 are constant, suppose these are two constant, and assume that phi1 of s and phi2 of s. So this phi1 and phi2 s are Laplace transform of f1 of t and f2 of t. So these are the values of Laplace transformation of f1 of t and f2 of t, which are denoted by phi1 and phi2. So then linearity property for inverse Laplace transformation says that inverse Laplace transformation of k1 phi1 of s plus this is k2, then phi2 of s is equal to k1 time. So this is inverse Laplace transformation of phi1 of s plus this is k2 time inverse Laplace transformation of phi2 of s. So this is called as linearity property of the inverse Laplace transformation. So this property says that sum of their inverse Laplace transformation is equal to sum of their inverse Laplace transformation. So and while taking the inverse Laplace transformation, we may take the constant term outside the inverse Laplace transformation. So this is very important property for finding the inverse Laplace transformation. Now to understand this linearity property for this inverse Laplace transformation, let's discuss the example. So suppose first example is if we wish to find out the inverse Laplace transformation of, suppose this is 1 upon s plus 4 plus this is 1 upon s raised to 6, then we can write this as 1 upon, suppose this is s square minus 16 plus, suppose this is s square s upon this is s square plus 25. So now to find out the inverse Laplace transformation of this term. So now we may write somewhere as constant, suppose this is 5, so for understanding this property better. So now this is the example where we have to apply the concept of inverse Laplace transformation. So observe that while taking the inverse Laplace transformation, this is the first term, this is second term, this is third term, and this is fourth term. So according to the linear property, this linearity property, so if sum of term is there for the inverse Laplace transformation, then we can write there sum of inverse Laplace transformation. So according to this linearity property, so we can write this as inverse Laplace transformation of, this is 5 upon s plus 4, this is the first term, plus this is inverse Laplace transformation of 1 upon s raised to 6 plus this is inverse Laplace transformation of 1 upon s square minus 16 plus this is inverse Laplace transformation of s upon s square plus 25. So we write this step because of the linearity property of the Laplace transformation. So now observe that, so this is the first term. So in this first term, so if we observe the value of denominator, whenever we find the inverse Laplace transformation of any function, so try to concentrate on the denominator value. So denominator value is s plus 4. So if we compare with the standard result, so now this standard result is s minus 1, this is s plus a. So if we compare this concept with the second standard result, then value of a is 4, and where this numerator value 5, which is constant, so we can write this as 5, and then remaining term is inverse Laplace transformation of 1 upon s plus 4. So according to this second property of inverse Laplace transformation, so we can write this as e raised to minus 4t. So because value of a is 4, and we can write this as e raised to minus 80, so e raised to minus 40. So then plus, so plus if we compare this second term, so if we compare this second term with the result number 8, so then here the value of n plus 1 is 6. N plus 1 is 6. So we can write this as 1 upon 5 factorial into e raised to 5. Because value of n plus 1 is 6, so we get the value of n as 5. So we can write this as 5 factorial upon into t raised to 5. Now if we compare this third term, so this is the third term, so s square minus 16 is there, numerator value is 1. So if we compare this result with hyperbolic function, so then we get the value of a as 4. So because 4 square is 16, so then because of this minus sign we can use hyperbolic function, and numerator value is 1. So we can write this as 1 upon a, which is 4, into this is sine h of 40, sine h of 40. Now again for this last term, if we compare this last term with hyperbolic, no, if we compare this last term with result number 6, then this is our type s upon s square plus a square. So where the value of a is 5, because of 5 square is 25, so value of a is 5. So we can write this as cos of 5t, because a is equal to 5. So in this way we can easily solve the example based on the inverse, based on the linearity property for the inverse Laplace transformation. So now this is the simple example. Now let's take the next example, which is based on the standard result 9, as well as which is based on the linearity property for the Laplace transformation. So now, so let's take the next example. So now next example is, so to find the example, so this is the second example, find inverse Laplace transform of, suppose this is 3s plus 4 upon this is s square plus 16. Now let's take the simple example so that your concept will get clear. So now if we apply the inverse Laplace transformation to this term, then we get this as 3s plus 4 divided by this is s square plus 16. Now friends, whenever we try to solve the example based on the inverse Laplace transformation, first concentrate on the denominator term. So now here denominator term is s square plus 16. So if we compare this denominator term with this standard result, then we get this as s square plus a square, again s square plus a square. Now but that means we can easily apply the concept of result number 4 as well as result number 6. That means result number 4 and 6 are applicable to find out the inverse Laplace transformation of this function. So but denominator is in our standard form, but numerator two terms are there, so we can split this into two terms. So this 3 is constant, so we can write this as inverse Laplace transformation of s upon s square plus 16 plus 4 is constant. Again we take the outside the inverse Laplace transformation. So inverse Laplace transformation of 1 upon this is s square plus 16. So we write this step according to the linearity property for the inverse Laplace transformation. So we just split this numerator into the two parts, and while splitting this into the two parts, we take constant term outside the inverse Laplace transformation. Now observe that this first term, so first term is s upon s square plus 16. So apply result number 6, s upon s square plus 16. So we can directly write the value of this term as 3. After comparing this to this result number 6, we get the value of a as 4, because 4 square is 16. So we can directly write the value of this term as cos of 40 plus this 4 is constant. Then if we compare this term, so if we compare this term with result number 4, then this is 1 upon s square plus a square, where the value of a square is 16, then again value of a is 4. So we can write this as 1 upon 4 into sine of 4t. So in this way we apply the concept which is called as a linearity property, as well as we apply the concept which is called as standard result for finding the inverse Laplace transformation. Now these are the simple examples. So this is our example number 2. Now let's take the third simple example, so which is based on this property. So now third example is, so if we wish to find out the inverse Laplace transformation of 2s minus 5 upon this is 4s square plus 25. So now let's try to find the inverse Laplace transformation of this function. So now we know that if we apply the inverse Laplace transformation concept, then we get this as 2s minus 5 upon this is 4s square plus 25. Now friends, observe that whenever we find the inverse Laplace transformation of any function, concentrate on denominator term. So if we compare this denominator term into the standard form, so then this denominator term will be in our standard form when 4 is absent from this term. That means if we remove the term 4, then we get the standard form of this inverse Laplace transformation. Then we can write this as, so this is the first term. If we split numerator into two parts, and after taking constant outside the inverse Laplace transformation, we can write this as 2 into inverse Laplace transformation of s upon this is 4s square plus 25. This is the first term, minus 5 into inverse Laplace transformation of this is 1 upon 4s square plus 25. So now we write this step according to the linearity property for the inverse Laplace transformation. But this, even though we split this into the two parts, but this equation is not in our standard form. So because in our standard form, this is of the type s square plus a square. Whenever s square plus a square terms are there, 4 results are applicable, first, second, third and 4 results. So these 4 results are applicable. But for all these 4 results, coefficient of s is 1. Coefficient of s is 1. Now here we get the value of coefficient of s as 4. Here also we get the coefficient of s as 4. Now according to the linearity property, take 4 outside the Laplace transformation. So we can write this as 2 upon 4 out after taking outside. We can write this as inverse Laplace transformation of s upon s square plus 25 upon 4. Similarly, we can write this as minus, this is after taking 4 common, we get this as 5 by 4 into inverse Laplace transformation of 1 upon s square plus 25 upon 4. So now, why we take this 4 outside the inverse Laplace transformation? Because we require coefficient of s square as 1. So now, let's rearrange this term so that we can apply one of these 4 results. Now here this is s square plus, we require the value of a square. So for your better understanding, I will write this as 2 upon 4, that means this is 1 upon 2. So we can directly write this value as 1 upon 2 into inverse Laplace transformation of s upon s square plus, how to write this 25 upon 4? So we can write this as 5 by 2 its square. Again, this is so this is minus, so middle sign is minus, so we can write this as minus 5 by 4 into inverse Laplace transformation of 1 upon s square plus, this is 5 upon 2 its square. Because after writing this 25 upon 4 as 5 upon 2, we get the standard form of this standard result. Now we can directly write the answer to this term as 1 upon 2. Now this is the standard result which is related to the cos term. So inverse Laplace transformation of s upon s square plus a square, which is cos of 80, where the value of a here, the value of a is 5 by 2. So value of a is 5 by 2. So we can write this as cos of 5 by 2t. Then this is minus 5 upon 4. Then again, if we compare this second term with this result number 4, this is going to have s 1 upon s square plus a square, 1 upon s square plus a square. Again, the value of a is 5 by 2. So we can write this as 1 upon a. 1 upon a means this is 1 upon 5 by 2 into sine of 5 by 2 into t. So this 5 will get cancelled, and after rearranging this term, we will reach to the final answer. So now, friends, in this way, we can apply the concept which is called as linearity property for the inverse Laplace transformation, as well as after applying this standard result for inverse Laplace transformation, we can easily solve any example based on the inverse Laplace transformation. So this is the first method for finding inverse Laplace transformation by standard result. So for your better understanding, so let's take some more example. So based on this method first, which is called as inverse Laplace transformation by standard result. Now let's take the fourth example. So this is our fourth example. So let's discuss the example number 4. So find inverse Laplace transformation of, suppose this is 4s plus 15 divided by, this is 16s square minus 25. So now let's take the somehow complicated example so that your idea will get clear. So if we take the inverse Laplace transformation of this term, then we get this as inverse Laplace transformation of 4s plus 15 divided by 16s square minus 25. So now according to the linearity property, so we can write this as 4 into inverse Laplace transformation of s upon 16s square minus 25 plus, this is 15 which is constant. So because of constant term, we can take outside the inverse Laplace transformation. So this is 1 upon 16s square minus 25. So this is, we write this step according to the linearity property for the inverse Laplace transformation. So but again, friends, to apply this standard result, we require the coefficient of s square as 1, because this is our like s square minus a square, so s upon s square minus a square, so we may apply this result s upon s square minus a square, but for this result we require the coefficient of s square as 1. So now to apply this result number 7, so we have to take 16 outside the inverse Laplace transformation. So we can write this as 16. Then this is inverse Laplace transformation of s upon s square minus 25 upon 16. This is the step after taking 16 common, plus this is 15 upon 16 into this is inverse Laplace transformation of 1 upon s square minus 25. Because so if we compare this result with s square minus a square with this term, we require coefficient of s square as 1. That's why once again we take 16 as constant, which is constant. After taking outside the inverse Laplace transformation, we will reach to this term. So now we will rearrange this term as 1 upon 4 for the 16 into inverse Laplace transformation of this is s upon s square minus 25 upon 4. So we require this value as a square. So we can write this as 5 upon 4 its square. Similarly, we can write this as 15 upon 16 into inverse Laplace transformation of 1 upon s square minus, so by default I mentioned this as 25, so 25 upon 16 is there. So we can write this as 5 upon 4 its square. So finally we will reach to the answer 1 upon 4. So this is the standard result for hyperbolic cos function. So we can write this as cos h of 5 by 4 t. So plus this is 15 by 16, then this is hyperbolic cos function for sine. So we can write this as sine h of 5 by 4 t into 1 upon a, so value of 1 upon a, so we can write this as 1 upon 5 by 4, and after taking reciprocal we can write this as 4 upon 5. So this 5 1 the 5, 5 3 the 15, 4 1 the 4, 4 4 the 16. So in this way we will reach to the final answer. So this is somehow complicated example, but for your understanding we take this example here so that your all ideas for applying these standard results and linear property will get clear. So friends, so these are some examples which we had discussed under the method 1. So this is the first method for finding the inverse Laplace transformation by standard result. So now let's take some examples for your practice purpose. So now to test your knowledge. So now let's take the example for your practice. Now friends, time is to test your knowledge. So now to test your knowledge, so total 11 examples are given. So these examples are very simple. So use this 9 standard result and linearity property to solve these results, and try to learn the first method, so which is called as inverse Laplace transformation by standard result. Here answers of these questions are not provided because these questions are very simple. So friends, I hope you like these lectures. So thanks one and all. Thank you.